Okay, so hello everyone. I am Marina, and I'll be there as tech support during the tutorial. I want to introduce you to our tutor, Jovan Bubonja. He's an applied scientist at TomTom, and he will hold the from RNNs to transformers, a journey through language modeling tutorial. Enjoy.
Okay, so hello everyone. First of all, maybe I could tell a little bit about myself. So professionally, I'm working as an applied scientist at TomTom. So lately I've been working with in the field not that related to language modeling, in the field of consumption modeling. So we're working with the consumption model of EV vehicles and trying to improve the range estimation and thereby improve your experience while using our navigation. But that said, I also had quite some experience with language modeling. During my internship, I was working particularly with language models. So yeah, I have some experience with them also. So maybe now I could share my screen and start the presentation. Okay. Maybe you could give me a heads up if the presentation isn't shared. So, sorry. Do you see the presentation screen? Sorry, can someone maybe...
Yeah, we can see the presentation, yes.
Okay, nice. Sorry for that. So to the topic of today's tutorial will be about language modeling, as the title suggests. So this tutorial will be more focused on, like, let's say, theory aspects of language modeling, but uh, don't be discouraged, because I think that the understanding the theory behind language modeling and building intuition behind how those models work could be quite beneficial for, I mean, every use case that you may encounter on your day-to-day job. So let's first start from some simple sorry. Okay, well, let's first start with the agenda. So we will first start by explaining what is the language representation and how do machines interpret and ingest the text that we input. So how do they transform the strings into something meaningful for them? Then we'll transition more to language modeling, go over some, let's say, historically important models such as neural language models, then transition to recurrent neural network models, and to the today's state of the art by adding attention mechanism, and then transitioning to transformers architecture that you're all well aware of. In the end, I will try to give a few simple explanations of how these models are trained. So the whole field of self-supervised learning is currently a hot topic amongst researchers. So maybe just a brief overview of all the techniques that are currently used, and then maybe talk about transfer learning. So maybe the most commonly used way of language modeling. So using the language models for some of your particular use cases. And in the end, we'll briefly talk about small language models and do we indeed need those large models that have over hundreds of billions of parameters? So, yeah. First of all, we need to talk about language representation. So, as you all know, we input strings to our language models, and we get strings as an output. But what does exactly happen inside it? So first of all, we would need to define these two steps for getting the model prepared to execute some stuff on our text. So first point would be the tokenization, and second step would be vectorization of our input. So so yeah, in order to get our computer to understand text, we need to break it down. So we need to convert it into something that is understandable to machines. The tokenization process might sound redundant, but it's very important for our language models because as we will see, like giving an input string as like, let's say, cheese burgers are great. It's all well and suited for our type of communication, but the machines such as our models, the neural networks, don't understand strings as given in this format. So we would need to figure a way to somehow reduce this text into meaningful units that maybe could be potentially processed by our models. And next step would be word tokenization, word vectorization, which indeed is converting those tokens into vector space. So basically, the only things that our neural networks know of are vectors. So we would need to figure way out how to embed these tokens into some, let's say, higher dimensional vector spaces where each word, let's say, cheeseburger, and let's say great, could live somewhere in this vector space and give a bit more meaning to what we're talking about. So let's start first by tokenization. The first and the simplest one is the character level tokenization. So let's take again the input sentence. Cheeseburgers are great. And the simplest way would be to divide this string by just dividing it to every single character. So how this string would look like would be like, first we would have the C, then the H, then we would have a double E, dot dot dot, and then till the end we come to E, A, T, and then the exclamation mark in the end. So this would be the simplest and, let's say, most atomic way that we could divide text, so in simple characters. And this type of tokenization has some benefits and also some cons to it. So first of all, by dividing text into characters, we would have a great way to deal with out of vocabulary words. So we can now add that as a plus. So out of vocabulary words. Uh, out of, sorry, out of vocabulary words. Next, it would also help us with handling misspelling. So if, let's say, maybe I forgot to input one E in the cheeseburger word, it wouldn't matter as much as for other tokenization methods. So next would be misspelling. Misspelling. And yeah, in some languages for some specific applications, the character level tokenization might be beneficial because dealing with languages that don't have clear word boundaries are quite hard for other tokenization methods. So let's maybe call it some specific applications. And yeah, so we could, let's say, list these three as the three major pros of the method. And there were also some quite big downfalls to this method. So first would be the computational complexity. By that, I mean for a language model to learn to produce text character by character, it would require quite a large amount of parameters in the model and also quite a lot of text to be trained on. So by specifying the model in this way, he would have no prior knowledge of any words that exist. So that would be definitely the biggest downfall of this method. Next would be, sorry. Next would be the word tokenization. So by this, we would split the given sentence into 4 different tokens. So first would be the cheeseburger. Next would be R. Great. Exclamation mark. So with this, we have now gained some semantic meaning to our text. So it captures the meaning of text by treating each word as a separate token. This should probably allow models to better understand each of these tokens and also the relationship between different words. Next, it should be noted that it is the most commonly used way of tokenizing words, so it is probably the most common. And also, as we said here, we had quite a lot in computational complexity. Here, the computational complexity is reduced by having a predefined vocabulary of words. So here the model doesn't have to learn each word character by character. We give it some predefined vocabulary, and hopefully it should result in a more efficient model, since it already has the knowledge of some semantic meaning of text. And last but not least, it's the, let's say, most complex maybe way to tokenize words. It's subword tokenization. Here we have 2 popular methods. So we have something called byte pair encoding. And second, it's called word piece tokenization. Okay, so first, byte pair encoding was proposed as a text compression algorithm, but logically enough, it was also very well suited as a tokenizer for language models. The idea of byte pair encoding is to divide sentences and sequences into subword units which appear frequently in the corpus. Let's first define the word corpus is some fancy way of calling your, let's say, data set in NLP, so natural language processing. So every time I mention corpus, it's a large set of text. So yeah, the way this tokenization method works is a little bit more complicated. So let's say we take 3 sentences. So she walked to the train station. Next, he is walking to work every day. And third, I took a walk to relax. So how this method works is, first of all, we would take all these sentences. So we define the small corpus of text. We would take all of these sentences and first divided on character level. Character level. And from there, we would take a set of all the unique characters. Unique characters in corpus. So we would basically have one instance of each letter contained in this corpus. Here comes the important step. After defining all the characters, we would go first through all the pairs of tokens. By this, we mean because we have defined tokens currently as characters only, we would go 2 by 2 characters and try to find most frequent. We would try to find the most frequent pairs of characters that are contained in this corpus. And by doing so, maybe first we would encounter that characters like W and A occur frequently together. So we would then go on and merge those two and create a new token, WA. Also, maybe we would find out also that character L and K also appear frequently together, and then we would use that and merge them to LK. These 2 new tokens would go into our token vocabulary, and then we repeat the process again. Now we don't only have the characters, but we also have some first iteration of tokens that we found in our corpus. So let's say maybe next step would be then that we found that again tokens WA and LK appear frequently together. Then we would go on and merge them to walk. And here we would encounter our first word that would go into our corpus. So step by step, iteratively, we would find many of these words together. But then what is the purpose of subword tokenization? It is to maybe in the case of, let's say, word walking, and the word walked, maybe we don't need to have both of these words in our corpus, in our vocabulary of tokens. Why? Because the root of the word, so word walk, is contained in both of these words, and it pretty much contains most of the meaning that this word carries. The suffixes of ing and ed also give some context, but maybe we should split them, because ed, when let's say squashed with any other word, let's say talk, then we get talked, it means that the event happened in the past. So maybe having these tokens, so the ing and ed would be it would be a good idea to have them as separate tokens and then combine them into new words. By using this, we then, this way of tokenizing, we further down reduce the size of our vocabulary. Which in turns, which should in turn yield a better and more efficient learning for the model that we define. So next part would be like when we decided, let's say maybe on using words or subword tokenization. Next step would be how to embed all those tokens into some meaningful vector space that the computer could understand. So the most basic thing we could do is to define those vectors and as one-hot vectors. So we would, let's say, take we would take some words. Maybe those words could be, let's say, a man, king, woman, and queen. And then we could also maybe use an apple and then orange. If we define words this way, we would end up with one-hot vectors. Let's say we have one hot vector for man. It would be, depending on, of course, the vocabulary, it would contain mostly nulls. And then in the place where the word man appears in the vocabulary, it would be 1. Again, we can do the same for word woman. Word woman should appear somewhere lower in the dictionary. And then we do that also for the word queen and king. And in the end, we do that for apple apple and orange. Apple would be somewhere along the top, let's say. And then we have the word orange. It would be somewhere in the middle, let's say. So by defining words this way, we did manage to bring our tokens into something that is much more understandable to our algorithm. But in turn, we didn't catch any semantic meaning between these words. By that, I mean, if we take a look at Euclidean distance between each of these vectors, we would see that, let's put it here. So let's say we would have a vector u and v, and we define Euclidean distance, something like this. We would then have a sum over all of the features that we have in our vector. And then just subtract accordingly. So we would end up with all of the vectors having the same Euclidean distance, which in turn doesn't help our model in figuring out what kind of information does the text carry. Also, a different way we could measure could be maybe the dot product or the cosine similarity. Basically, it boils down to the same thing. So if we wanted to check if two vectors, the cosine similarity of two vectors, we would take, basically the dot product would be included inside. So we would have to take the dot product between two vectors and then take the norm, the L2 norm of each of these two vectors so that we could normalize our input. By looking at the cosine similarity, we're basically just looking at the angles between our two vectors. So let's say if we took a vector man and the vector didn't write that accordingly. So if we took the vector man and the vector, let's say apple, we would see that by having all of these features being sparse, so only one feature being equal to one, we wouldn't gain any information. Between those two vectors, we would have a right angle. So basically the similarity would be null for each of these vectors. So the one-hot encoding isn't such a good idea of representing text. We would need something to define something new, something better, and we would like it to be, let's say, featureized representation, or maybe we can even call it a distributed representation. So the term distributed representation you will quite often encounter in fields of machine learning and deep learning, because it is the sole purpose of systems like neural networks to create a distributed representation of the inputs that we give so that we could much easily handle it and maybe do some, let's say, classification or or even do some generative approach on these vectors. So the better solution is to use something called word2vec. So first we would go and I forgot to check, but if there are any questions, just feel free to write it down in the chat. So I totally forgot to take a look. So in when talking about word2vec, we would try to define it a bit differently. So if we had a sentence, I want a glass of orange juice to go along with my cereal. We would maybe want to push this task as some kind of language modeling. So maybe if we were trying to figure out what could be the meaning of the language juice, maybe we could take that token or that token as a, let's say, target that we want to hit. And then we could take some other words from this sentence as a context. So maybe taking a glass of. So basically we would want to structure this problem as some kind of a learning problem. So by having a context as an input and then juice as a target, we would be more than prepared to define some newer algorithm to learn better representations of the word. So next, let's say we will use the one hot vectors just for the purposes of learning. So we would want to learn a embedding matrix E, and then by multiplying this embedding matrix with some one hot word vector such as O of man, we would want to end up with a distributed representation of that word embedding of a man. So we would we would start by, let's say, inputting our words. So a glass and of, and then transform it like this, multiply our embedding matrix with, let's say, a vector of O, glass, and of. And then we would try to input it into our neural network. Here we would have some hidden layers. And in the end, we would like our neural network to produce, again, some vector that would contain the probabilities of each word in our vocabulary being the right one. So maybe we would want other words to have low probabilities. And then when we get to word juice, we would like to have a higher probability of that word appearing next. This is the way that we would like to formulate this problem. So by having this, we would then define a loss function and have it be some kind of a cross entropy where we would take the correct input and multiply it by the logarithm of the desired output. By structuring the learning this way, we would want to in turn learn this embedding matrix E. So the primary focus won't be on learning the parameters of the neural network. We will definitely need them, but the end product that we need is this embedding matrix E. In the end, the paper that published the word to vector algorithm had quite remarkable results. So maybe if we would plot the vectors in some low dimensional space. So we would get something like, let's say, having a man plotted somewhere here. Woman would be also nearby. Then at the other end of the spectrum, maybe we would have the word apple and the word orange. And then somewhere here we would have a vector king and the vector queen. And the results, as I said, are quite remarkable. As we can see, like typically the outputs of these the sizes and the dimensions of these vectors are quite large, maybe some, let's say, 300 dimensional vector. And we, of course, we cannot visualize it, but using some of the modern methods for projecting higher dimensional spaces to, let's say, the low dimensional plane as this is the 2D space, you can maybe take a look at methods like t-SNE and also UMAP if you're interested about it. We can see that the words are grouped together nicely. So we have maybe in this sector of the vector space, we would maybe find fruits. And then in this part, we would find anything that is, let's say, human related. Also, what is another awesome thing about this vector representation is that by knowing in what kind of relationship these two vectors, let's say man and woman are, and king and queen, we could also do a search on this vector space. So by by subtracting the value of the vector E man by the E woman and adding the value of, let's say, E king, we could find the word E queen in this vector space. So this is quite remarkable, and this shows that this representation has a lot of knowledge about the semantic meaning of words. Now that we have such a nice way to represent our words, we can go forward into the language modeling part. So we could, let me check if there are any questions. No questions still. So yeah, we need to touch about some more important bullet points in language modeling. So first of all, it's quite a different problem than, let's say, the image processing or computer vision stuff, because it can have variable length. So the sequences that we produce, sentences, can have. Okay, sorry, someone raised his hand. Yeah, sorry. So this has become quite a problem with recent language models. So the gender bias, or uh, if maybe I haven't understood how can the problem with gender assignment avoided in vectorization? Sorry, could you please rephrase the question? Okay, so I will continue and then we'll see. We'll try to answer the question. So unlike the fixed length data commonly processed by traditional algorithms, so text can have a varying length. So this is one problem that we have to be aware of. Also, the hierarchical structure. Language exhibits this hierarchical structure where words form phrases, and then phrases can be sequenced into sentences. Capturing this hierarchical organization is of essence to language modeling. Also, the ambiguity and the context sensitivity. Human language is inherently ambiguous, so we often rely on context to add some meaning to the words. So depending on where in the phrase the word is located, we can have quite a different meaning of the word. Yeah. So next, the thing that we should mention is the syntax and grammar, the structured nature of language, governed by syntax and grammar, further complicates the task. So effective language representation models must capture the syntactic relationship between words. Also, the semantic understanding, as we already talked about, beyond the syntax, achieving a nuanced, let's say, grasp of semantics is imperative. And then also their creative compositionality and temporal dynamics, which we won't be talking about too much today. Oops, sorry. Yeah. So let's talk about a bit about neural language models. So let me check again the Q&A. Okay, so using vectorization, the words are clubbed into vectors to use them. Our language is always double-sided. For example, orange is both color and fruit. King is a oh, okay, I now understand the question, and we will be answering that part in the coming slides. So when we talk about the attention mechanism, and you will see there is quite an awesome way that we can deal with that stuff. So that was a great question. Thank you. So yeah, okay, so the neural language model. Let's again say we have sorry, didn't switch it to pen. Let's again say we have the sentence, I want a glass of orange juice. And we have figured out a way how to tokenize and vectorize all of these words. We would then go on and create again the structure that we used previously. So we would have the I, maybe we would use the word level tokenization, and then we end up with something like this. Glass of and then we just input everything into some vector space. So we have the one hot vector of I, the one hot vector of want, and one hot vector of juice. Next, we multiply that with the embedding matrix. And we end up with the embeddings for these words again. If we wanted to learn something similar of the stuff that we see today that the modern language models do, such as ChatGPT, we would need to structure our learning task as the prediction of the next most likely word. So if we were to mask the word juice and leave it as an open space, we would want to input everything except the last word juice and input it into some kind of a neural network. Let's say we have some simple version of a neural network. Maybe we only have one hidden layer or something like that. And from there, we have the output, which would be the softmax over our, let's say, maybe 10,000 word vocabulary. So what is the problem with the neural language models defined this way? First of all, defining it like this, so with a fully connected neural network. It would imply that the input would have to be of fixed length. And that is not acceptable. As we know, you can input text with variable length. So this is the first reason why this is not a great idea to use a fully connected neural network. Next, the problem would be the computational efficiency. So even though we reduced it by tokenizing and vectorizing these words, we relieve the pressure that the model has in terms of, let's say, having to have, I don't know, billions and billions of parameters, but then we can reduce this even more. How can we do this? That step would come next, as we would talk about recurrent neural networks. So it is a form of an autoregressive model. That means that the input that we get from, let's say, the last time step gets inputted into the same module as before. So let me share my, sorry. So okay, take the pen. Let's start. So you would have some kind of a, let's say, a black box here, which would be our recurrent module. We would have a input, maybe some input vector that would be an embedding of some word, let's say en, some unknown word. And from here, we would have some output predictions. And also from here, we would have a feedback loop that goes back into our module. So if we unwrap this architecture, we would have like a series of these black boxes, which would in turn be quite useful for having input of variable length. So if we input here, let's say glass, and then off, and we input here orange, we can somehow propagate the context of the words and hopefully produce something that we would expect, such as the word juice. So by having a single recurrent module, we can reuse the parameters. So we can leverage something that is called parameter sharing. So we reuse some of our weights. So we basically say that probably these weights would be as useful as for the word glass as at some position in the sentence. So maybe it was at start of the sentence. So probably the same weights would be useful regardless of the position in the sentence where they were used. And then we have let's say a more nuanced version of this, which is the something called LSTM module, or long short term memory, where we go into this black box, which is the recurrent module, and we found out like how does it look like. So first of all, we will be getting some context here from our previous from our previous computation, so from the previous module. So we will maybe annotate it like this. Let's say context of the previous time step t plus t minus 1. From here, we would be getting the input. So as we said, some vector embedding of, I don't know, some word at some time step. I mean, not sometimes, this time step. And then we will need to explain how this intricate system inside works. Sorry, this would be the activation of the context. The context would be coming in through here. So here, these yellow boxes with the letter sigma in them is what we call gates. And in the LSTM module, we have 3 gates. So basically, we have a forget gate. Then we have an update gate. And in the end, we have output gate. And each of these gates is parameterized by some set of weights. So we could denote it as W forget, W update, and W output. So this would be the set of parameters that this model learns. How would we calculate the output from this? So basically, we have a word coming in together with the activation of the previous module, so the A of t minus 1. We would first maybe put it through the forget gate. So maybe some of the context that we've got from the previous time steps is maybe not quite useful with regards to the new word that we have at this time point as an input. So putting the activation and the embedding through this gate and then multiplying it with our previous context would give us a refreshed version of stuff that we want to convey. Next, we would then again pass the activation and the current vector that we got and pass it. Okay, maybe I need to write this down. So this is the forget gate, and this would be the update gate, and this would be the output gate. From the update gate, as the name suggests, we would want to update the context. So we thrown out some, maybe we could let's just something we throw out as garbage, and then we would like to update the context with some new meaning. From this part, the 10H activation, we will be getting the refreshed context. So the update gate will figure out which part of the new refreshed context we would like to pass, and the 10H part would be responsible for computing this new context. So maybe we could denote it as C tilde at this time space T. With this new context, and by update gate regulating which parts of that context should pass, we would like to sum that up with all the stuff that we got from the previous words. And that would mostly be the context that we pass forward to our next modules. For the output unit, we just want to figure out so which is the most important part, so the most direct activation that we would want, so that again we could continue in the same process. So the activation should be indicative of so which part of the context should be forgotten or updated and stuff like that. This tanh part is just we just use the current context, pass it through the tanh activation, and then forward it as our new activation. So A of T. Here we have the context at our time step, and if the model is structured this way, so maybe if it's some translation problem, we can immediately output some word. Maybe no, it wouldn't be an embedding. It would be some probability over our vocabulary. So where we could find the word with the highest probability. And this is pretty much it, how we control the context. So what is like really great about the LSTMs module is that we have this, which we can call the context highway. So let's just write it down, the context highway, in which information can flow without any obstruction. So maybe some context as from that we got from previous words such as glass could be, and in this example is pretty indicative of what word should be chosen next. So glass and juice should be like pretty close in the language model's decision space, let's say. But the big problem here is that the linear nature of these LSTMs can, if we encounter long sequences of text, it can lose context on previous words. So the solution and what has created the big boom in regards of language modeling is the attention mechanism. So this image here was taken from the attention is all you need paper, and it denotes how the whole attention mechanism works. So first, let's try and dissect this equation. Here we have a few interesting matrices. So we have the query matrix Q, we have the key matrix K, and the value matrix V. A great analogy with these three matrices, so the query, key, and value can be the problem of database search. So this is where the names of these three matrices come from. So if we want to search a database, you would need to input a query. So the stuff that you would want to get out of it, basically you would need to provide a key. So maybe if you were looking for some particular entries in some table, you would input also a key, and in the end you would get the value as the output. Let's translate that to our neural network. So first of all, we have the matrix multiplication between Q and K. So basically these two matrices, what they do is that they do a linear transformation of the space that we have. So in turn, here we chose a word, I forgot to write down. So the two words that we chose, yeah, sorry, the two sentences that we chose would be maybe I bought an Apple phone, and the other sentence would be maybe, I don't know, apples and oranges are delicious. So here, if we would to do some language modeling, as we had a previous question, so how would we discern between Apple as a tech brand and Apple as a fruit? So basically, we would need to somehow transform the vector space in which those words are represented, given the context that we have. So that's where the attention mechanism comes into play. By transforming the, let's say this would be our initial vector space. And here we could see that maybe this is where the word phone would lie, and this is where the word orange would be, and let's say somewhere in the middle would be the word apple. So as we see here, it denotes either the fruit or the tech company. By having the keys and queries transform the space, we could then figure out a better way to separate the vector with regards to the context. So we would basically want to move the word apple along this line in the context of first sentence. We would move it more towards the word phone, so that our model understands that we are talking about the tech company. And in the second sentence, we would want to move it maybe towards some cluster of fruits that are defined in the vector space, so that it knows that we're talking specifically about fruits. In the end, the value matrix gives us an internal representation that is valuable to the model. So basically, we would want to, from this space where it is quite clear to see that these two subjects are completely divided. So let's say the technology space and the fruit space, maybe in the internal representation of the model, it's not that far away, but we would like to bring it back to something again that is meaningful to our model. So in turn, we end up with again some linear transformation of space, but that is then more meaningful to our model and to the task of next word prediction. Again, so we end up with, by stacking multiple of these tension heads, we get to the transformers architecture. So basically, we would have multiple sets of multiple sets of query key value matrices, each looking at maybe a different relationship inside the sentence. So if we maybe come up with some sentence like this orange is not ripe. Maybe one of these key value query matrices sets would look at, let's say, the word orange and try to correlate it with word ripe, so that it understands that the orange in this context is not ripe. And then also maybe a second layer. So as we see here, we have three attention heads. We have here three attention heads, so maybe one set would be looking at the relationship between the word orange and the word ripe and give it high attention. And maybe the other layer would look at the dependency of, let's say, not ripe, so that given the meaning that orange in term is not ripe. So multiple layers of this attention mechanism is what gives the today's state-of-the-art models the appeal and the usefulness that we want to use them every day. In turn, we see here that regarding the, let's say, the context or the heads, we also, as we said, first we scale the vector space, and then at some point we would want to give it some attention. So maybe at this layer there is more meaning carried, so we would want to emphasize the dependency that this attention head has managed to get. So yeah, this is basically the answer to the question that we had in the chat. So how to discern between the meaning that a single word can have in multiple different contexts. And for the end, we would gloss over some of the self-supervised learning problems and tasks. So just a second. So first of all, there is masked language modeling. So it is the approach that we were looking at. So we would like to, I would like a glass of orange juice, we would basically just mask some of the words in the context and make the model predict the most likely words that could come at that place in the sequence. So basically, the next word prediction is basically the mask language modeling tasks. So from here, we could just mask this part of the sentence and ask the model to predict how does this sentence finish. But then, of course, we could maybe do it differently. So the first approach, the next word prediction, is maybe more used by models like the GPT and the masking of multiple words. So maybe we would mask the words wood and glass are more commonly used by models like BERT. So these are two models that you can check out if you're more interested about language modeling. Also, the next sentence prediction, or this is also a commonly used technique. So if we would take the sentence, I need to relax, and then take a pair for this sentence. Let's say maybe I should take a walk. The next sentence precision would take these sentence pairs and structure the learning so that we predict the likelihood of, let's say, the sentence, maybe I should take a walk. So what is the probability of that sentence coming after the one I need to relax? So by this, by structuring the learning task like this, we would capture the meaning and the context in which these two words, these two sentences could be found. So the permutation language modeling also is quite simple. So if we do some kind of permutation, so maybe we take this sentence and say, like, we randomize the order of these words and then say orange and then I dot 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 dot, and in the end we have a. We would like our model to predict the correct ordering of the words. And this again would give our language model, the ability to understand the context of the corpus that we are training it on. And for the end, it is the contrastive learning. Here we would we would have a, let's say, a positive sample and a negative sample. And we would like to increase the difference between these two, let's say, in our case, these two sentences. So that is pretty much it on self-supervised learning. As for the transfer learning, maybe the most most used way, or the way in which we mostly use these language models. Maybe we could have something like text classification. So maybe we would want to classify our emails into, let's say, emails that have positive meaning, and maybe some that have negative meaning, so that we would want to omit sending emails with negative sentiment. Second of all is the named entity recognition. So maybe this would be useful if we have some large document that has like many pages, and we would like to find some specific entity in that document. So maybe we have maybe something related to car warranty. We would like to find some service intervals that we need, our car to be maintained. So we would just put it through a language model, and hopefully as the output we would get something like each year you need to service your car. Language translation, one of the most popular use cases for language models. So it's the case where we need to translate, let's say, maybe an English sentence to let's say, German language. Maybe you went to a vacation to Germany and you do not know how to, you've encountered some person that doesn't know English, so you would like to translate the text and give it in German. And for the end, question answering could also be a useful task, and it is a part of how the models like ChatGPT are trained. So we want to train them so that it can give us some useful answers. And all of these tasks are performed by transfer learning. So we have a language model that we've trained maybe by masking some input words, and a simple learning technique like this one, so masking the input, can give us such a rich representation and interpretation of text for these downstream tasks, such as task classification or language translation or question answering. So this would be pretty much it for today's lecture. I hope that you found some answers and maybe gained some intuition on how the language modeling and in general how text processing in natural language processing works. Yeah, so maybe if there are any questions for the end, I would like to answer these questions. So maybe some useful reference book. So basically, best way to learn all of this stuff would be by basically searching the internet and finding some relevant courses from some let's say, universities that are highly regarded in that topic. So maybe taking a look at something like Stanford University online courses would be a good starting point. Also on Coursera, you can find a load of very useful courses. So maybe for someone who is more maybe for some more beginner friendly courses, I would recommend the machine learning specialization on Coursera. So yeah, basically that would be a great point to start. Also, we have a question from Marco. Since you talked about language model, what LLM do you prefer to use? So yeah, that is quite a good question. So I use ChatGPT on a daily basis, and yeah, it has become an integral part of my day-to-day work. So yeah, thank you to everyone who was watching the presentation, and hopefully, yeah, I was able to give you some intuitive explanation on the whole language modeling topic. Maybe if the moderator could jump in. Okay, then we will be closing this session. Again, thanks for everyone who joined, and hopefully I will have the opportunity to see and meet you at Data Science Conference in Belgrade. Thank you very much.
Thank you, Jovan, for this tutorial. It was very interesting, and thanks to everyone for listening. Bye.
Thank you. Goodbye.